Hi, everybody. Welcome to our physics colloquium for this week. This week, we're being joined by Professor Suzanne White-Brahmia, who's going to tell us about her work in physics education research related to physics quantitative literacy. And I'll introduce her briefly. So Professor White-Brahmia is an associate professor with the physics education group at the University of Washington in Seattle. She's been teaching physics at the middle school through university levels for her entire career, which started in the Peace Corps in Gabon. Her research focuses on students' conceptual mathematics reasoning development in the context of physics. Before joining the faculty at Washington in 2017, Dr. White-Brahmia directed the extended physics program at Rutgers for over 20 years, teaching a physics course designed to promote learning and persistence in engineering for groups underrepresented in engineering. She's published papers on physics mathematization and on bridging the ethnicity and gender gaps in engineering in the American Journal of Physics, Physics Review Letters, and the Journal of College Science Teaching. She's served in many leadership positions in physics education research and with the APS, and she currently is a co-chair of the College Board AP Physics 1 Development Committee, where she helps lead the development of the AP Physics 1 exams. We're very happy to have her here with us virtually today to tell us about measuring and enhancing quantitative reasoning in physics instruction. If you have any questions during the talk, you can submit them in the Q&A or chat by text at the bottom of your screen. And I will read them out for Suzanne, and so we can do questions throughout the talk. I think that's it for me, so take it away.
Okay, great. Thank you for that introduction, and thank you for inviting me. I would also like to thank the NSF for supporting this work, and my co-authors and collaborators. I'll be discussing a variety of things, and it's been a lot of people over a number of years who've contributed to developing these things. Just a shout out to my research group at the University of Washington, the Physics Education Group, started by Lillian McDermott. It's the first physics education group, and lots of support and help over the years from this group of people. The quantitative literacy, timely. People confuse flattening the curve with eliminating the coronavirus, which is something I think we're all familiar with hearing. Global issues are increasingly dependent on quantitative reasoning, and medical decisions are quantitative. The medical schools have increased emphasis on calculatorless quantitative reasoning in their admission process to meet this need. Engineering and scientists routinely use quantities in their of rates of change in the physical world, and there's mounting evidence that, first off, it's very hard to learn, and many don't understand them. This is a learned skill that happens over the years that they're studying. Physics can help as a discipline because quantitative reasoning in introductory physics is characterized by using simple mathematics in creative and novel ways. And I'm going to discuss that in more detail in this talk. Here's an example. Our equations tell stories. If you just look at that equation, we probably all have a shared experience of what we think it's describing because we're all physicists. We quickly construct a mental story about a covariation between the position and the time that a projectile is in motion, that it's starting 40 meters above the ground and launched with the speed of 5 meters per second vertically downward. The downward we get from the coordinate system is set by the 9.8 meters per second squared, which we all recognize as being the acceleration due to gravity. Downward is its direction, so negative must mean the downward direction. Part of the challenge of learning physics is developing the ability to decode symbolic representations in this manner. And the reasoning is with middle school mathematics, which is ubiquitous in all STEM fields. Facility with rate reasoning is essential, and it's challenging. We've coined the term physics quantitative literacy, meaning using familiar mathematics in distinct ways to understand and interpret the world in the context of physics. We think of it as being a blend, so a mental blend in our heads of conceptual and procedural mathematics to generate and apply models relating physics quantities to each other. There's mounting evidence that students struggle to conceptualize arithmetic and algebra that's used in introductory physics, and that these difficulties carry over into subsequent course taking. In a summary of studies on upper division physics students by Caballero and colleagues, they saw that by synthesizing many studies, that students struggle to activate appropriate mathematical tools without prompting, to recognize the meaning of mathematical expressions, spontaneously reflect on the results, and especially to generate expressions from a physical description. It's not that it's hard for majors to do these things. They generally don't struggle with executing the mathematics, but they would like to understand what they're doing and why they're doing what they do. So in this talk, I'm going to describe a probe that we've developed to try and assess physics quantitative literacy, called the Physics Inventory of Quantitative Literacy. I'm going to share what we've learned about student reasoning using this probe, and discuss some potential pathways to more expertise building on student resources, depending on the amount of time at the end of this talk. So what does that mean to build on student resources? The sort of prevailing model of thinking in the physics education research community is that knowledge is made up of pieces, and the pieces could be fairly small. So there might be a little chunk of knowledge there that doesn't look to an instructor like the student knows what they're doing, but it's there and can be built on. And so the idea is to understand what those student resources are, and then also understand what the expert resources look like and how they're connected to each other, and then develop materials that bring the student into a more expert-like framework. And what I'll first talk about is the probe that we've developed that allows us to sort of understand better where the students are at, called the Physics Inventory of Quantitative Literacy. And it's built on a history of other inventories that have been developed that may be more familiar to you, like the force concept inventory or the mechanics baseline test. Many other physics contexts that we've seen concept inventories developed over the years. But there's little research into how physics quantitative literacy develops over the course of a typical introductory physics sequence. And I emphasize that I'm going to call this the PIQL, because that's its acronym, that the PIQL is a reasoning inventory that probes the quantification typically used in introductory physics. So it isn't targeted at a specific moment in time of the concepts that students are learning in a particular course, but it's the reasoning that they do with the quantities that they're learning about. It's an instrument that is strongly influenced by two theoretical frameworks. One of them is, and that this has to do with the expert knowledge space. How is expert knowledge structured in an expert's head? And this framework is conceptual blending. And the idea, I'll discuss it in a minute, is that the mathematics and physics are intertwined for an expert. The other framework that's important here is the test construct, which is about what is it that the test is designed to measure. And we lean on the work of Bruce Sharon in symbolic forms, and I will discuss that briefly also. So what is a conceptual blend? One approach that has had gained some leverage over the last few years, or last decades actually, is to think about mathematics could add some physics examples in as applied calculus, for example, or applied mathematics. You learn the math, and then maybe problem number 32, 33, and 34 have some sort of physics context associated with them. That's one model. Or in the introductory physics course, we can talk about conceptual physics and social physics, and then we have a few problems where they're just doing some calculus in that. We argue that those are not effective either at integrating the mathematics and the physics. And because fundamentally, in an expert's head, the mathematics and the physics are blended so tightly, you can't pick apart when you're doing math and when you're doing physics. And so what we really see is this completely blended chunk of stuff that people are doing. The test construct. So Bruce Sharon did work with students at Northwestern University, which is a selective university in the United States. And what he did was to observe them. They're in their third semester of calculus-based physics, observe what groups of students do at the board when they're solving problems, how they interact with each other, the kinds of thinking that they do. And when they're successful, he documented the sorts of thinking that they were exhibiting and created a library of what he calls symbolic forms. And I'll describe those presently. But what he says in that work is that successful physics students learn to understand what equations say in a fundamental sense. They have a feel for expressions, and this understanding guides their work. We do students a disservice by treating physics conceptual understanding as separate from the use of the mathematical notations. So what does that look like? Here's an example. So you can think about, here's an example where an object is falling at terminal velocity and the students set up this, the net force there is equal to 0. You've got two things canceling each other out. But that mathematical structure could just as well be used for, say, a isothermal process in the first law of thermodynamics. We have this sense in physics, this balancing thing, and it's a structure that we see over and over again, and we call on readily. So that would be a canceling symbolic form. Most students who take introductory physics are less sophisticated than the students that were observed in Sharon's study and come from less privileged backgrounds. We consider symbolic forms to be an objective of teaching introductory physics, and the PIQL is designed to help probe, to use as a probe to help researchers and instructors meet the objective. Are the students reasoning in these ways? The PIQL is a multiple choice test designed to probe sophisticated reasoning with simple mathematics. It's administered as a pre and post test, and the relative quantity is gain. So how much have students gained in a particular course? The questions are either single correct or multiple select correct answers, and it takes students about 40 minutes to complete, and it can be administered online. I'm going to show a couple examples and relate it to the symbolic forms. So I'll let you go ahead and just read this question. Okay, and this is an example of the ratio symbolic form where we create a quantity, we generate a quantity that is something different than either the base or the height that tells us something about steepness. And there's the symbolic form right there for that. Here's another example. Again, I'll let you go ahead and read. And this is an example of a quantity symbolic form that I published about, in which our quantities in physics have a value. Typically, we can expect that they fit into this structure. They have a value, they have units and a sign. Sometimes they don't have a sign, and sometimes they don't have units, but the vast majority do. And so we would have an expectation of there being a sign and that that sign has meaning in this context. everything is given by the first sentence that it's a vector quantity. So as students learn to think in terms of vector and scalar quantities, they start to get better at questions like these. So how do we operationalize PIQL? The process of characterizing a system so that it has some sort of unit of measure, that quantity symbolic form. Quantification is central to physics, and the quantities are what are sort of the actors in our models. So here's an example. If the motion is characterized by 9.8 meters per second squared, what does the value 9.8 represent here? And I'll let you go ahead and just think about that for a minute. And it gets a little bit easier if we think about it by breaking the units down to what they actually are, namely 9.8 meters per second in each second. So this is giving us a unit rate that the speed will change by 9.8 meters per second in each second. We could just as well characterize the motion in this way. So in this context, what does the value of 0.1 represent? And I want you to feel what's going on in your brain as you try to make sense of this. And again, we can break down the units to what they really mean. And come up with a unit rate that it would take 0.1 seconds for the velocity to change, or the speed to change by 1 meter per second. The first is very familiar, the second is unfamiliar, and the second is what it feels like for students every single time we introduce a new physical quantity in our classes. They're making sense in real time of something they've never seen before. So we've broken down this process of modeling to 3 important areas. One is proportional reasoning, which I think everybody's familiar with, using ratios to describe systems, and we do it a lot in physics, a lot more than any other discipline does at the introductory level. Covariational reasoning may not be a term you've heard before, but I'll describe it presently so you get a sense of what that is. But we hold in our mind these invariant relationships between quantities in dynamic situations. So how does the position change as a function of time, for example? And then reasoning about signed quantities, as we've seen in these previous examples. Covariational reasoning, when we say to students, it goes like 1 over r squared. We know what we mean, but it's a weird thing to say, and it's not a thing that they say in math class. What I've learned by working with mathematicians is even that proportionality symbol gets a lot, gets way more used in physics than in math. And I recently gave a talk and somebody said, a mathematician said, "What's that fish?" So these things we do that we think of as being math are physics math already. And that notion of covariational reasoning, what is it we're doing? Mass is understood to be unlikely to change in this context, that G is a constant. And so we only see the R squared. We only see that covariational relationship. All the other things just sort of disappear in our minds. The first stage of this is to understand how experts think about covariational reasoning, how proportional reasoning, how they're using that. And they're useful for assessment design, instructors, and curriculum developers and research. So we have put some time into interviewing experts and really trying to understand and characterize how they think, how expert knowledge is structured. Published a paper on the natures of negativity in introductory physics. And we're in the process of developing natures of proportional reasoning and natures of covariational reasoning. It's really useful for experts to understand how they think, because we usually don't think about it very much.
So there's a question from Jason Harlow. He says, I think this is the force concept inventory, the FCI, is designed to be readable by the layperson. meaning that students taking their first physics course can understand it in the pre-course. The PIQL looks like it has a lot more jargon. How do students react to getting a physics test before the course starts?
So I'd encourage you, Jason, to look at the whole PIQL. I showed you the electric field question. That is the one that depends most on physics knowledge. Almost the entire rest of the test doesn't in any way. So I would argue that it's less, it's a lower barrier to entry than the FCI is in that regard. Go ahead and take. If you Google it, you'll find it on Physboard. It's available, so you could look at it and see that. Okay, thanks for that question, though. But we don't. We don't expect students to ace it from the get-go. It isn't a thing we can't take the physics out of it, because the physics and math are, the difficulty is the blend, that conceptual blend. Thanks for that. Okay. So I'm going to use some terms, speaking of jargon, so that I don't lose people along the way. When I talk about an inventory, I mean a test. Items are test questions, and test construct is what the test measures, okay? So this is just some of the standard stuff you want to look at when you're looking at validity of a test. And thank you, Carol. And we have gotten some great CTT results with the test. The test retest reliability meets the criteria both for groups and individuals. And I'm going to show you some information about the difficulty and discrimination. Difficulty is aptly named as being the opposite of what it is. The higher the difficulty, the easier the question. It's basically the percentage correct that students get on an item. And you want to make sure that the boundaries that you shoot for are between 0.2 and 0.8. We consider the population with whom this has been validated, the University of Washington students in the calculus-based physics course, to be a pretty selective group. So we are fine with having items on this test that have a higher difficulty than 0.8. So what this represents is, as you go up in the scale, those are the different versions that we've gone through on the PIQL, and version 2.2 is the published version. So you can see initially we had some items that were too easy. We got up to the top of difficulty. If you look at version 2.2, almost all items except one falls within the 0.2 to 0.8 boundary. And discrimination it tells you for each item how well it predicts whether, so if students who do well on the test do well on that item, and students who do poorly on the test do poorly on that item, then that would have a very high discrimination. And so you want the discrimination to be we shot for 0.3 above, and we've made that with the final version. So this is a well-validated instrument. What have we learned about student reasoning? The first is that what you're looking at here is 121, 122, 123. That's mechanics, E&M, and waves at the University of Washington, calculus-based course. The students take the test at the beginning of each quarter. So what we're looking at is the pre-test for 121, the pre-test. So the pre-test for mechanics, pre-test for E&M, pre-test for waves. The pre-test for E&M serves as a post-test for mechanics, and pre-test for waves serves as a post-test for E&M. And what we see is that there is very little improvement as a function of having taken a physics course. So the kind of reasoning, stop and think about this for a minute, the kind of reasoning we use every single day when we talk to our students, when we present models, when we look at how this changes with that, they're not getting any better at it just by whatever it is that we're doing. What this is a matched set. So these are the same students as they go through the entire sequence. This is the course grade as a function of their PIQL pretest score before they take the first test. So this is in the mechanics course. We looked at how does the course grade correlate with what their pretest score was on the PIQL. And I see here that the correlation coefficient didn't show up on my slide. I'm sorry. So the slope on this is 0.39 plus or minus 0.02, which is considered correlation. Question, do you think it's meaningful? Yes. The question is, do you think it's meaningful that the standard deviation is increasing as they take more courses? Yes. I'll go back to that slide and tell you what I think is going on here. I think, and this is just a hypothesis right now, I think that students who were already students who are already doing well do better, and students who weren't don't change. And so I think we end up getting a bimodal distribution as we go further along in the courses. We're looking into that more now. So I do think it's significant that the standard deviation is getting bigger. That's one explanation, but I don't have evidence beyond, this is very preliminary. This is very scattered data right now. Thanks for that question. Okay, so the slope here is roughly 0.4. It's 0.39 plus or minus 0.02, which is considered correlated in educational research. As it's a good correlation. So there's some predictive value with the PIQL as to what the final grade in a physics course is going to be. Through some more sophisticated analysis, which I won't go into deeply, one factor analysis and module analysis, even though we've built up the test out of 3 different frameworks: proportional reasoning, covariational reasoning, and negativity. From the student's perspective, it's a unidimensional instrument. This is in supports this notion that there's this thing of physics quantitative literacy, and that these make up those parts, even though an expert would be able to differentiate between those things. But we do see some patterns emerging. I don't expect you to see what those little squares are, but I want you to see this pattern. Item tree analysis takes each of the items and connects them. So, for example, this is an item, it's a fish item you haven't seen. Students need to get that right in order to get the next ones right. And so this would be the easiest item. And then there's these pathways, these reasoning pathways through here. And we're using this analysis to try and understand how this kind of reasoning clusters. What's interesting here, the 2 items I've already shown you. Actually, I showed you slide, right? Yeah. And that shows up here. So that's sort of middle range easiness. And then I'm going to show you the 2 that are down here, which are really the most difficult. And the bottom one is considered the most difficult item on this instrument. This is the second most difficult. If you want to think about that, I'll let you go ahead and read this one. I think we all recognize that this is something we do all the time in our courses. And here's another one, please. And I would like you to read this one carefully. Also, it's the last one I'll make you read today. Okay, so this is the most difficult question. And I'm going to go into some reasons why that is. But the difference we see between experts and novices is novices get this correct maybe at 50% or lower, picking if there's equal percentage picking D or E. Experts also do that, but they do one more thing. They ask themselves, does it make sense? And they have techniques for doing that. They might use units, they might plug numbers in, they might look at limiting cases, all sorts of things they might do. But novices don't do that, and experts do. So it isn't that experts get the correct answer immediately. It's that they narrow it down and then they start using techniques for making sense. And that's where we really see the difference between novices and experts, is that sense-making piece is missing. It's not part of their epistemology about what you do when you solve a problem. Okay, so although we didn't see much change in the difficulty getting better over the quarters, what this is the four questions. These are the 4 questions that I showed you in that item tree analysis. And the dark color is the pre-value, and so the dark blue and the dark orange, and the lighter color is the post. And what we see happening here is, even though the difficulty, so meaning the percentage correct, I'm going to say that the percentage correct gets better or slightly worse, even though that's probably not statistically significant. We see a pattern in that the discrimination gets better. And that is what supports what my response to Paul was, that if the discrimination is getting better, it means kind of the rich are getting richer and the poor are getting poorer. Namely, those who are doing well on these questions are doing well on the test overall, and those who are doing poorly on these questions. So we see the discrimination getting better with the test, which to me is an indicator of, supports this hypothesis that there's a spreading, that that some students are getting better at this, and some students are getting worse. So it isn't that we're ignoring them, we're actually possibly doing harm. We are not doing no harm. If this hypothesis pans out, it means if some group's getting better and the average isn't changing, somebody's got to be getting worse. Okay, so what are some potential pathways to build more expertise? Building on student resources. Here's some patterns we're seeing. We see that rather than making ratios for comparisons, which is pretty common in physics, like if we want to compare things in physics, we usually make a ratio. And part of that is because we're used to dealing with quantities that may differ by large orders of magnitude. But the average person goes to subtraction as a way of comparing two things. So this go-to of creating ratios for comparisons isn't necessarily in their toolkit and isn't necessarily familiar. Forming multiplicative structures. So when we create a quantity like momentum and we understand it to be something different than the mass and the velocity, students focus in on one of those two. They tend to focus in, they have a hard time differentiating between momentum and velocity, for example. When we create ratios, like with the slide, a very popular incorrect answers was to either focus on the height of the slide or the width of the slide when thinking about steepness. But that process of creating a new multiplicative structure is a step beyond. The quantities represented as general variables. That's why the odometer problem is so hard. That's why, because we have a general variable, meaning we had a height h instead of a height that was a numeric value. And we do this all the time when we solve problems. We just make a general variable. We'll have a block of mass m. That automatically will make that problem harder for the students to understand. And then what I mentioned about evaluating merits of competing strategies at the end, at that odometer question, experts get it down to it's either this or this. And then they have ways of reasoning about it where they unanimously land on the correct answer. So those with student difficulties, and I don't want to be a Debbie Downer here, students have resources that we can build on too. One is this notion of compiled relationships. So the good news in physics is we only use about 5 functions and we use them over and over and over again. So if we can bring students into that ballgame, then we're good. And they do have some functions they come up with that they'll go to. One of them is the Pythagorean theorem, another is an inverse function, but they're not as familiar with, say, a decaying exponential or a quadratic as they are with these that they've learned before they get here. They have reliable algorithmic and ratio reasoning with whole numbers, and I'll demonstrate that to you in a minute, and simple unit analysis, but that is also an emerging skill. So here's an example of, oh yeah, I'm going to ask you to read one more. This is an experiment that we did. I did at Rutgers and then I replicated with a graduate student at the University of Washington. So I'll let you go ahead and read the question. Okay. And the correct answer is that, again, forming a unit rate, how many cups of rice for each cup of milk. Okay, we asked this question, we separated it out, and the different versions are here. This is the exact same question. I'm not going to ask you to read it, but what we did was we replaced, in the first one you just saw, 4 pints of milk and 2 cups of rice. We used fractions and decimals here, 0.575 pints of milk and 5/8 cups of rice. And then in this context, we use a variable, n pints of milk and 5/8 cups of rice. And students were randomly assigned one of these versions. And here's the results. Okay. So if they got the whole number version, they saturated that question. If they get up to 85%, then the rest of it is kind of noise. So that they knew how to do it. They were able to do it. But if we replace that with decimals and fractions, it made it a little bit more challenging. But if just one quantity was a general variable, they were less than half of the students got that correct. So the use of variable is non-trivial, and we should think about it and think about the barrier to entry for our students when we are doing that in our classes. So what are some of the pathways we might use to get using student resources? So for example, building on the differences comparison. If an instructor understands that the students coming in are familiar with using difference as a comparison, they may make it explicit that ratio is something we do in physics a lot to make comparisons, ratio, and kind of build that into the discourse that they have with the students, have an expectation that that would be a new thing that they would be doing. Positive and negative represents position on a number line. That's students' experience. That's their unique experience with positive and negative numbers before they come into our classes. And we use positive and negative numbers to mean so many different things. It's incumbent upon us to signal when we're using a positive and negative sign in a way that may not be familiar to them. They're familiar with X and Y as variables. If you look in a math book, the 97% of the variables in a math book are X and Y. And we use many different quantities and variables, and a quantity might become a variable in a problem and a constant in another problem. And it is helpful and useful for students to start, at least that they understand that this is part of what they need to learn how to do. It's useful for us to understand that students aren't there yet when they get to our class, regardless of how much math they've taken. What's next? Assess beyond the introductory course. We're in the process of doing that. So we're giving this test up. We've just given it in a course in the 200 level and 300 level. They're still not saturating the test. So we want to know, where does that kind of reasoning develop and how does it develop? We want to look at different institutions. So if anybody's interested in giving it here, we would love to have you give this test. We're looking at characterizing student knowledge space and growth in the way that I showed you with the item tree analysis, and then developing instructional interventions to help develop this kind of reasoning. This is also a question of equity, in my opinion, that who are we excluding? If this is indeed a bimodal distribution, and there's a lot to indicate that maybe what's going on. We see some nice correlation up here. And then what about these guys down here? What's going on when you get less than 50% of these correct on the PIQL? What about these students here? If this is indeed becoming a bimodal distribution by the time they get to the third semester, the third quarter, what about the lower mode? Could we be doing more to keep those students engaged and helping them succeed in our courses? And so
there's another question from Jason, which is, how do faculty do on the PIQL?
Thank you for that question. Okay, we've given it to faculty, and that's such a great question, to faculty and to the and graduate students. And actually, the graduate students do best. The faculty, there is this thing, okay? There's a thing that when you use a certain math tool to do a certain thing all the time, you start to become you start to think that's the only way you can do it. And so there's one question on the PIQL where you could do it by finding the area under the curve or comparing areas under the curve. But you could also do it by just looking at the axes and making sense of what the quantities are. And that's what we expect the students to do. But we've had faculty who take that question and say, you can't do this unless you know calculus. It's like, well, no, people forget how to do some of the simpler things. They don't realize what they're doing. They don't remember what it is to not do that. So faculty do fine, but they do take a little while to reason through it and then discuss it with us. Great question. Okay, so if we want to think about what about that lower mode, remember this is designed and validated with students in calculus-based physics and at a select institution. Charlotte Zimmerman, who's a graduate student working with me, is working on a gherkin, which is a version of the PIQL for the algebra-based or pre-calculus before you get there. So there's no, all of the functions are linear, and there are no vector questions about vector quantities in it. And that we will be targeting high school instruction as well as college. And we're working with pre-college teachers to try and understand how they're thinking about this. Because remember, most people teaching physics, at least in the United States, their degree was probably in the natural sciences, probably biology is the most common. So if we're thinking about who's teaching, we're also thinking about how are they doing on this kind of thing and how much do they value it. So there's a hand up, right?
Yes, we're not taking live questions right now, but because it's being recorded and then put up later. But if you can type your question in the chat or in the Q&A, and then we can read it.
Great. Okay. And so this will allow us to assess that kind of PIQL, physics quantitative literacy at all levels, and also illustrate to pre-college instructors the kind of reasoning that's experts consider valuable when students get into their college level courses. And these are some interventions that we're working on right now. I'll just show you, that's all I can really do in the time we have. Physics invention tasks, I have a whole website of those, which are all about students put in the position of constructing quantities. So it's there's a lot of philosophy behind that of constructivism, that students generate the physical quantities before they learn about them formally, so that they have some sort of structures to hold that onto. Laboratory interventions are really great for covariational reasoning because of the linearization of data. That's exactly what we're doing. What does this go like? One of my graduate students is working on a virtual reality laboratory interventions that promote hypothesis generating and testing. And in this hypothesis generating, students are, again, looking at the covariation between quantities that they're measuring. And the STEM fluency platform. So I'll just show you these briefly. So what I'm going to do is stop this share and share a different thing. There it is. Okay. Okay. So these are the physics invention tasks that you can easily Google and find at the University of Washington. And there's the background on them here, which you can read about if you'd like. I just want to show you that there are lots of them. There's a password that goes along with this, which is treehouse, oops, the capital T. And we have, I'll show you an example of a task so you can get a sense of what that's like. So this would be a task that they would do before they learn about acceleration. And you turn your head sideways. They're just very simple. You've got cars. The speed that the car is going is up above the car. And then there are these little drips of oil. The cars drip oil every second. And we ask the students to figure out if the cars are made by the same manufacturer. So that the task is each a car manufacturer makes cars that speed up in exactly the same way. And so we want them to quantify some sort of speeding up index with that. And more challenging than you think. I've given this to students after they've had formal instruction on acceleration and they struggled with it. So it's hard. Generating things is hard. STEM Fluency is a platform that Andrew Heckler has put together at the University, Ohio State University. And what this does is students have targeted questions that they need to, it's mastery level learning. So they answer questions as part of homework that are very targeted on one specific skill. So here's one which is probably familiar to you, the covariational reasoning between energy and speed. And so then they do increasingly more sophisticated questions, but they're really just to get them to do that kind of thinking, that covariational thinking, reasoning. And then the last one is this. I'll just let you watch this video. This is Jared describing his virtual reality.
In NOMR labs, students work with simulations of familiar and unfamiliar physical phenomena in an immersive 3D environment. For example, the first scenario students use has virtual analogs of positive and negative charged particles which obey Coulomb's law. Like real particles, like charges repel, opposites attract, and together, many charges can be used to observe emergent large-scale behaviors and create complex, stable structures. Then students encounter Menti particles. These do not exist in our universe, we made them up. There is only one type of Menti particle, and they repel each other at close range and attract at long range. Left alone, they undergo a semblance of simple harmonic oscillation. Students often propose that the force between two Minty particles is directly proportional to their separation, like masses separated by a spring. However, closer inspection with quantitative distance and force measurement tools eventually reveals that the force goes as 1 over the separation, but with a constant offset. Minty particles are one of several fictitious physical phenomena used in NOMR labs. For example, one scenario has 3 different types of charge, as opposed to the 2 we're familiar with, that interact with each other in distinct ways. Another has a force law that seems to depend more on relative velocity than on relative position.
Okay, let's stop sharing that. And